The focus of today's lecture is really on black holes, but not only that. I've drawn here a picture of a black hole, which I suppose everyone has some idea of. Everyone's heard of a black hole. Essentially, it's a region of space which is very, very condensed, and there is sort of a surface of the black hole called the event horizon right here, and inside that area you'll find that no signal, no light, no information, no infinitely powerful rocket could get you out. You will be trapped there forever, so hence we say black holes, no exit. So for example, I've drawn a picture of a poor astronaut who's fallen in, crying help, but his colleagues in the spaceship are unable to hear him because no information can get out. On the other hand, he can receive information from his colleagues. They could be sending information down there saying, where are you, where are you? He'll get that information. So it's a sort of a one-way membrane. Once you're inside the black hole, you can't send things out, but you can still receive things coming in. So just as a kind of a prelude to the rest of the talk, I'm going to be explaining this basic phenomenon of a black hole. I'm going to be telling you about signals that you actually can get from near the black hole that would allow us to detect black holes, say in the next 5 years. That would be a very exciting discovery if we can actually find signals from a black hole. And break the talk up into 4 parts. The first one is explaining Einstein's theory of relativity. Turns out, although it's very complicated in mathematical description, it's based on very simple ideas. And that's the one thing I want to drive home here, is that most great works in science, and physics is no exception, are based on very simple ideas, although sometimes the mathematics that describes them can be kind of complicated. So I want to get that point across. And then I'm going to explain in more detail what black holes are and what gravitational waves are, another prediction of Einstein's that there should be gravitational waves. But it turns out that because the theory is rather complicated in detail, we don't really have a good way of solving it. So we have to use very powerful computers to find solutions to Einstein's equations of gravity, known as general relativity. So it turns out, lucky for us, at this time, computers are now so powerful compared to what they were a few years ago that we at last have some hope of solving the Einstein equations for the first time. And at the very end, I'm going to show you some movies of simulations we've done of black holes that have been highly distorted or 2 black holes colliding. So I think what I'm going to try to do is put my transparency here so people can have a chance to see them in case I go through too quickly. Okay, one thing, as I've already alluded to, black holes are a hot item in the public imagination, in the public press. That is, you hear about them all the time. Here's an example of a calculation that was done by our group, and I'll show you a movie a little bit later of this particular calculation, but this shows how the space-time is very curved near the surface of the black hole. Very strong curvature, and Paul talked about this a few minutes ago about Euclidean geometry. It turns out Euclidean geometry has to be extended in a strong gravitational field to include curved surfaces. So you've probably all heard about curved space-time, and here's a picture of it. And I'm going to explain this in a little bit more detail. And you'll see this actually evolving in time in the movie. So, okay, I won't have time to go into as much detail about everything as I would like, but I would like to encourage everyone who has access to a computer network to take a look at our World Wide Web server. We have, at this particular address, can everyone read that? It's http://Jean-Luc, as in the captain of the Enterprise, .ncsa.uiuc.edu, okay? And what we have here is a series of different exhibits that you can go into when you connect to that page. You can find out about other groups working in relativity, about the people in our group. We don't really have the crew of the Enterprise, but we like to think of ourselves as sort of space explorers. We have information, movies, and this is one particular point that I'd like you to take a look at. If you look at our web server, we have created some very detailed exhibits on Einstein and numerical relativity. And there's one in particular that hasn't yet been opened, but it will be in about 2 weeks. And it explains Einstein's theory and black holes at a very introductory level. And it's very, very extensive. And I hope that everyone will get some benefit out of that. So now I think I will move on and start talking about some of the physics. And I would really encourage people to interrupt me with questions once I get going, because there's some really interesting brain teasers here, and I hope that people really think about these things, and please ask me questions. So this is really the heart of it. I'm going to tell you the basic ideas of Einstein's theory and show really what it was that made Einstein such a great genius in the history of physics. Because relativity theory is only one of his great contributions to physics. He actually won a Nobel Prize, as you probably all know, but not for relativity. He actually won it for something that led to really the basic idea of quantum mechanics, the photoelectric effect. But I won't have time to talk about that. I just want to talk about relativity today. Now, there's this idea that relativity is so complicated, you have to be a genius to understand it. It's absolutely not true. But there were a lot of comments, particularly in the early days, that made people have this sort of mystique about the theory of relativity. For example, there was an astrophysicist named Arthur Eddington in the early part of the century, and he was once asked by some reporters, Sir Arthur Eddington, is it true that only 3 people in the world understand the theory of relativity? And he said, who's the third? Implying that only he and Einstein himself could actually understand this theory. But I really want to make sure that it's clear they're very simple ideas. Now I want to tell you what they are. First, there was the idea of special relativity. This is what Einstein's first theory was of relativity, that he published around 1905 or 1906, I forget the exact date. And he meant, when he said special relativity, he wanted to understand what's the physics that people would measure in different frames. And by a frame, I mean we're all in one frame of reference. We're sitting here, standing, we're not moving with respect to each other. And we would do experiments and then measure, try to determine what the local physics is, like how fast a ball would drop, how fast a ball would move if we threw it, and so forth. On the other hand, you could imagine someone in a train moving along at a constant speed. Let's imagine they've closed the windows, and it's a very, very smooth track. So it's just moving along at constant speed. The windows are closed. It's absolutely smooth. You can't tell that you're moving if you're in that train. On the other hand, people on the side of the train track will see you moving along, so you're actually in different frames. So he wanted to see what's the difference in physics that people would measure in those 2 different frames. Okay? Now, it turns out that the laws of nature are the same, as you would expect, because you can't tell that you're moving. Okay? So that's kind of an obvious point, but Einstein made it a sort of a fundamental idea in his theory of relativity. So nothing terribly earth-shattering yet. But there's another thing. It turns out that if you were to shine a light, so there's a train here going down the track, right? It's coming along, and there's a light at the end of the track. There's a flashlight, and there are photons coming out of this flashlight, and they're coming toward the train, and they're coming toward somebody standing on the side of the tracks. Now, these 2 people do experiments, and they try to measure the speed of those photons. Now, imagine you're in a car, and you were driving along, and somebody stood on the side of the road, and they threw a baseball towards you, okay? What do you think the relative speed of the baseball would be when it comes to you? It would be the speed of the baseball that the person threw. So he throws it, say, as a pitcher, so he does 100 miles an hour. It's a fastball. But then you're also driving towards that fastball at, say, 60 miles an hour. So the speed of that baseball coming at you, you would think to be 160 miles an hour. It's just plain common sense, right? So, but there's something very strange that happens with a photon. It turns out you always measure the same speed, no matter how fast you're traveling towards the source of the photon. So we know that the speed of light through measurements is about 3 times 10 to the 10th centimeters per second. It's very, very fast, but it's not infinite. So if you're driving towards a flashlight at, say, 90% the speed of light, so let's say you're going 2 or almost 3 times 10 to the 10th centimeters per second, or that's 186,000 miles per second. That's how fast it is. Then you would still measure the same speed of that photon. And if you were standing still, you would also measure the same speed. So that seems very bizarre, and it seems very strange, but it turns out to be true. So if you put these 2 facts together, then it turns out that there are some very, very interesting effects. And Einstein was the one to figure this out. He said, okay, we know that the speed of light is the same for all people, regardless of how fast they're moving, right? And we also know that a speed is really a distance divided by time. It's how far something goes divided by how long it takes for it to move that distance. Okay? So, if it's really going to be the same regardless of the motion to the source, then something strange has to happen. And it turns out if you require those 2 things to be true, that the laws of physics are the same and you measure the speed of light to be the same regardless of how you're moving, that the way we measure distances and times have to change in some way with respect to the way we're moving. And it turns out that moving clocks go slow and moving rulers shrink. Now, it's not just an optical illusion, it's an actual fact, and you can do lots of experiments to see that this is actually true. For example, some particles have a lifetime. So let's say there's a particle called a muon that has a lifetime of, I don't remember now, I think it's 2.2 microseconds. That means this particle lives that long and then it decays into other particles, and you can measure that in a laboratory. But it turns out if the particle is flying very, very fast, say in an accelerator, nearly the speed of light, and you measure its lifetime, it turns out it lives much longer than that. And you can measure that. So therefore, its clock and its actual passage of time is different from what it would be if it were standing still. So you see, the passage of time actually changes depending, the rate of the passage of time changes depending on your motion. And also, moving rulers shrink. Now you see, both of these effects have to be true in order to kind of preserve that the speed of light would remain constant, regardless of all of your frame of reference. So, if I say moving rulers shrink, that means if I were to sort of throw this out into the audience at very high speed, say nearly the speed of light, and you try to do measurements to see how long it would be, you'd find it gets really contracted. And it gets really shrunk, and it's not just an optical illusion, but it actually contracts along the direction of motion.
But it would not be able to hit light speed.
Pardon me?
It would not be able to hit light speed.
It wouldn't be able to hit the speed of light, right, because it turns out that also implicit in the mathematics of all this, that the speed of light is a fundamental limit for all particles. Only a massless particle, that is a photon, or a particle that has no mass, can actually travel at the speed of light. Everything else has to go slower. Yes? There are a couple of different concepts of mass. There is an idea of mass increasing, and there's also the idea of a sort of a fundamental rest mass. And the rest mass is the fundamental concept. So yeah, you can think of it as having a larger effective mass as it moves as well. But the rest mass is sort of the invariant measure of the mass. That is, if it's in a rest frame, what is its mass? Okay? Now, I want to just... Oh, another question. Yes. Will its density increase? Its density, yes, its density will change as well as a function of the motion. Yeah, all of these kinds of properties that we take for granted as being sort of absolute measurements, absolute intrinsic properties of things, change because of special relativity. Okay? Now, I want to just pose a little brain teaser. Has anyone heard of the twin paradox? It's a famous story, not a story, but a famous paradox in relativity theory. And essentially, it works like this. You have two identical twins standing right here. And one of them says, let's test this theory of relativity. So I'm going to go in a rocket, and I'm going to fly near the speed of light away from the Earth, and I'm going to come back. And I'm going to see if I'm going to be any younger than you are. Because in principle, if I'm in a rocket going very fast, my clock should slow down. And when I come back, I should be younger than you are. He says to his brother. The brother says, well, wait a minute. From my point of view, I'm just sitting, you are actually, I can think of you as being at rest, and I can imagine that the whole Earth just moved away and then came back, and then therefore I should be younger than you are, right? So there seems to be a certain symmetry there, and you'd say, well, wait a minute, this relativity theory is nonsense, because how can time, it's going to look like the other guy is going, his clock is going at a different rate, but then when it comes back, if it's completely symmetric, how can it possibly be true? Okay? Now, can anybody think of a reason why that's not actually a completely symmetric situation? Go ahead. As if you had a third point of reference? From a third point of reference, they could look to be symmetric. But from the real answer is, from the point of view of the person who's in the rocket ship, say the brother who goes out, he's going to actually feel forces that push him. For example, when he accelerates away from the Earth, he'll feel, as the rocket ship accelerates away, he'll feel really pressed back against the seat as the thing's really taking off. Then when he gets out there, he has to stop and turn around and come back, and then he'll feel himself slowing down and then coming back. Whereas the person on the Earth always feels that he's in the same frame of reference the whole time. He never feels any any forces on him because of accelerations. So the point is that there is a break in the symmetry of the situation because the person who's in the rocket feels accelerations. And it turns out when he comes back, he will be younger than the one who stayed on the Earth. Okay? So that's the kind of the resolution to the twin paradox. I mean, I haven't explained exactly how it works, but the point is that it does work. And there have been experiments done like this where they take very accurate atomic clocks, they put them on an airplane, they fly them around at very high speed, and they bring them back, and they measure against twin clocks that were on the Earth, and they do find a difference in the time, just as predicted by Einstein's theory. Okay, there are lots and lots of brain teasers about this that I could explain, and I can talk to you all about afterwards if you'd like, but I probably need to move on. Okay, so those are some of the basic ideas about special relativity, but it was special, and Einstein realized it was special in that it doesn't include a gravitational field at all. So Einstein thought about this for a long time, about 10 years, before he came up with a way to include the same kinds of mathematical description of nature, but with a gravitational field. So he then called that his general theory of relativity. And this is really a truly awesome achievement, because it was so far away from what everyone else was thinking at the time, and yet Einstein just sat at a desk, essentially, and thought about it and thought about it, and thought, just what are the basic ideas? What's the basic law of nature that I have to come up with? And he realized what that was, and then he came up with a mathematical theory to explain that. So I want to then tell you about the couple of basic ideas. And the main one for general relativity is called the equivalence principle. Okay? Now, the idea is that if you're in an accelerated frame of reference, that is, if you're accelerating, it's exactly the same as being in a gravitational field. And in fact, that they're actually equivalent to each other. Okay? Now, what that really means is, here is Newton sitting by a tree, and suddenly an apple falls off the tree and hits him on the head, and he thinks about a theory of gravity. On the other hand, so that guy is in a gravitational field, right? Because he's sitting there, and you know that gravity is pulling you down to the Earth right now. You can feel your weight. On the other hand, if you're in a rocket ship and it's accelerating, I've tried to draw a picture of somebody who's being forced back. So he feels himself being forced back against the seat, and that is an accelerated frame of reference. It feels just like a gravitational field because you just sort of feel the weight of being accelerated forward, right? So you all know that if you're in your car, just think about it. You start accelerating and you feel yourself being pushed back into the seat a little bit. I mean, you don't want to, unless you have a Maserati or something, you won't feel it too bad. So Einstein said there's no experiment that you could do that could distinguish Newton sitting under a tree having an apple coming down and somebody in a rocket ship that's accelerating. Now, the acceleration is the key. If he's moving at a constant speed, he doesn't feel it. But if he's accelerating, that is, his velocity is changing, increasing or decreasing with time, then you feel yourself being pushed back. Or if you slam on the brakes and there's sort of an acceleration where you sort of feel yourself being forced forward. Okay? Now, there's another little thought experiment that I'd like you all to do. Think about it for just a second. If you have a helium balloon in your car, so you're out on Green Street, do this experiment. You can do it, this afternoon if you want. Put a helium balloon in your car, and you get at a stoplight, and you want to make a measurement of the helium balloon. Then the light turns green, and you start to go forward. Okay? Now I want you to think about what's the helium balloon going to do. So why don't everybody just sort of talk to their neighbor for a second and think about this for like 15 seconds, and then let's come up with the solution to this. Okay, so what? Who has an idea about this? It's going to go forward. Right. How many people got that? See, the basic reason, normally you think everything in the car is going to feel an acceleration, you're going to feel like you want to go backwards because the car is accelerating. But the helium balloon sees itself as being in a gravitational field. It's just like being in a gravitational field, but instead of one that's pulling it down, it's kind of a horizontal gravitational field from the point of view of the helium balloon. So the helium balloon feels like, hey, it's lighter than the rest of the air in that car, so it's going to move forward. And it's pretty astounding. I mean, I tried this the first time I heard about it. I got a helium balloon and drove in my car, and it turned out it really does. It goes forward, and when everything else in the car is sort of being pushed backward. And that's the basic idea of the equivalence principle, right, in action there. that an accelerated frame of reference is just like a gravitational field. Now, immediately, there are some interesting things that just come out of the basic concept because, for example, there's the bending of light. The bending of light by gravity comes out of this basic thought experiment because light you don't always think of as being something that would be attracted by a gravitational field, but it was one of the first predictions of Einstein's theory, and it turns out to be true, and you can see why just by imagining a simple experiment here with an elevator. The elevator here is accelerating upward, and you have a little flashlight and you send photons across. Now, if the elevator starts accelerating up, then these photons, because the elevator will be going a little bit faster after each second, the photons are going across and they're going up with a constant speed, they will be bent down. And you'll see that they will then take a path like this. Now, that's just the same as a gravitational field. Therefore, a gravitational field will bend the paths of light. And that turns out to be crucial in understanding how a black hole works as well. All right? Now, there's one more of these thought experiments that I want to go through, and then you'll have the basic ideas behind the theory of general relativity. All right, now I apologize for my artwork, but that's just the best I could do. Okay, another thought experiment. Now imagine you're at a merry-go-round, or perhaps a thing that I remember when I was a kid, a ride called the rotor, where you're in this room, it's a round room, and everybody stands up against the wall, okay? And then the thing starts to spin, and it spins around really fast, and everyone feels himself being pushed up against the wall, okay? Then the floor drops down, and you're sort of suspended up against the wall because of the centrifugal force pushing you, and you will not slide down unless, in fact, when I did it, I had a nylon jacket, and there wasn't enough friction to hold me up, so I sort of slowly slid down. I remember this very, very vividly from when I was about 12 years old. So anyway, the point is you feel this force, and it's exactly like a force of gravity. And I want to just go through the logic of how this works. Now, just remember, from special relativity, we know moving clocks go slow, and length contracts along the direction of motion. So we have to remember these two facts and then analyze what each of three people will see here, and then you can understand the basic idea of general relativity. For example, there's somebody standing at the very center of the rotor, okay? And let's imagine he's on a swivel, so the thing's moving around and he's not spinning, he's just sitting there watching things go around. Okay, now there's another person, the attendant is standing outside, and he's just taking people's tickets, but he's not moving at all. And then here you are, getting dizzy, going around in a circle, feeling that force of gravity now, not just, it's like a force of gravity, and Einstein said it's actually equivalent to the force of gravity. And we want to see what each of these people measures in terms of time and distance. Now, the person here is not moving with respect to the person here, right? Because he's just at the center, and he's at the same distance away always from the attendant. So these two guys don't feel any forces, and they don't feel, and they're not moving with respect to each other, so they must measure the same thing, according to Einstein. And it makes sense. I mean, we'd all agree with that. Now, on the other hand, you are moving around and going around and around and around, and the person who's the attendant here is going to measure differences in time and lengths compared to what you see because you guys are moving with respect to each other, right? So that's special relativity at work. On the other hand, A and B are actually not moving with respect to each other. For example, you could imagine A kind of rotating around at the same speed as B, and he's just, your guys are kind of locked together like this, looking at each other, but there's no movement along the direction of motion between you two at all. The only thing you feel at all that's any difference is the man at the center feels no force, but you feel that gravitational force pushing you out. So what happens is that clock B, we know it goes slower than C because B is moving with respect to C, so therefore it must also go slower than A, because A and C, we already established, measure exactly the same. And also, rulers, for example, the ruler A between these two guys doesn't contract, but this ruler that B is carrying with him does, because he's in equivalently in a gravitational field. This is the actual thought experiment that Einstein did, and it was published in his first paper on general relativity. In fact, it's a very readable paper. I read it when I was an undergraduate. So if any of you have access to it, you might find it kind of amusing to see you can actually read a paper by Einstein and understand a good part of it. So the point is, the bottom line of all this is that clocks in a gravitational field slow down, And gravity causes a warp in space-time. That is, it changes the lengths between things. So if you're near a very, very strong gravitational field, like near a black hole, and you try to do measurements, you'll find out that the Euclidean geometry you know and love from high school is no longer true. It has to be modified in some way. Okay? Any questions about that? Because I know that's, it's kind of confusing, but it's basically a simple idea just carried out to its logical conclusion. Okay. So that's one of the things that I want everybody to remember. Just burn this into your brain, that gravitational fields change the way that space and time are measured. Not just the way they're measured, but they change the basic nature of space and time. Now, I want to explain a little bit about what a force is in these two theories. That is Newton's theory, the old theory. Remember, force, Newton had an idea that force was proportional to the product of the two masses divided by the mass, or the distance between them squared. You may or may not know this, but it's a simple formula, and Newton realized that that's the gravitational force between two objects. So if they get very far apart, the force goes down. If they have very large masses, the force goes up. But it was just sort of a phenomenological law well, he actually derived it by looking at the orbits after sort of following up on the work of Kepler. But there's not really an underlying theory as to why exactly it is that way. But Einstein had a simpler idea that explained really what's going on. He said mass is sort of equivalent to curvature of space-time. It causes a curvature in space-time. And objects should do the most natural thing. They should move in the straightest possible path between 2 points. Now that's kind of a conjecture, but it's a very simple, satisfying conjecture. And let me give you an example of why that would lead to objects moving in a curved path. As we were just hearing about this morning, the distance between 2 points A and B you can determine by using the Pythagorean theorem by measuring the distance sort of perpendicular and the distance along this direction, and then squaring it, take the square root, and you get the distance there. But in a plane, like on the surface of this transparency, we know it's just a straight line, and it's just Euclidean geometry. But if you had a curved space, that is, measurements get curved because of gravity, then the straightest path will not look like a straight line necessarily. It may be curved. And here's an example. Here's the surface of a sphere. This sphere has now 2 points on it, A and B. You can't go through the sphere. That's no fair. You have to stay on the surface of the sphere, and that's a curved surface. And you can see the straightest path is actually a curved line that goes like that, all right? And the point is that gravity warps space and time, and it causes differences in the way paths move, or in the way objects move, because the space-time has been warped or curved in that way. Okay? Now, there were some very famous tests that Einstein predicted, or came up with, to test his theory. He said, okay, light should be bent by the sun. And there was a famous experiment done in 1919 by Arthur Eddington and others. They went to Africa, there was a solar eclipse, and they measured the positions of stars whose light should be just coming by, right by the surface of the sun. So here's the sun. There's a star here. The light from the sun, from that star, goes by the sun, and it gets curved. It bends in that way. And then the person here measuring it thinks the star actually came from this direction because they can't see the whole path. And that way, by measuring the positions of stars, you could tell that light was actually bent by the sun, and it turned out to be exactly right. He also solved a long-standing problem about the orbit of Mercury. It turned out it wasn't exactly like what Newton would have predicted. There was some discrepancy, and Einstein's theory worked beautifully to explain that. And there are other tests, but one thing that I'm going to focus on now is gravitational waves and black holes. So, what is a gravitational wave? Now, this is something, yet another thing that came out of Einstein's theory, was completely unexpected, is that there should be something called gravitational waves that propagate through space-time. So, if you know electromagnetic theory, which you probably don't yet, but someday you'll study this, I'm sure, there's a basic idea that if you take a charged particle like an electron and you accelerate it back and forth, you sort of can imagine shaking loose some photons, and then they fly away because of the motion of that object. And we know that that's true because, for example, we have light bulbs and we have electrons moving through, actually heating up and then emitting light rays. So there's a thing called electromagnetic radiation that comes from the motion of charged particles. We have the same thing in or in general relativity that says if you take masses and you move them around, they will emit waves, not electromagnetic waves, but a completely new kind of wave, radiation, called gravitational waves. These waves have never been detected, but they've been predicted now for many, many years. And it's another very confusing subject that for many years people weren't sure if gravitational waves were real or if they were just some artifact of the mathematics, because it was very complicated. And even Einstein himself had a proof, he thought, that gravitational waves were not real after about 20 years after he had published his theory. So there was a big debate, a huge debate in the community about whether waves were real. Arthur Eddington had a comment and said he didn't believe in them, and he said gravitational waves propagate at the speed of thought, because he thought they were just a figment of people's imagination. But it turned out that about 30 years ago now, people proved theoretically, at least, that there should be these waves, that there was no doubt there should really be these waves. And the way you get them is if you have large masses moving at high speeds, then you'll get more and more radiation. So the faster things move, the larger the mass, the more radiation you get. So we need to look for these radiation sources. One of them is a so-called binary pulsar. Has anyone heard of the binary pulsar? Okay, what do you know about it? Just two big stars orbiting about each other. One of them is a pulsar, which is a neutron star that's emitting a certain signal, not gravitational radiation, but there's an electromagnetic pulse that comes out. And it turns out that these two stars are orbiting about each other very, very, very fast. Because of that motion, they're emitting gravitational waves. The gravitational waves are carrying energy away from that system, so the orbit is decaying. Just like in Star Trek, you might notice sometimes, you know, they're orbiting about a planet and their orbit's decaying and because they're losing energy, right? It's exactly the same thing. And it turns out that this binary pulsar system has been measured and studied from the point of view of relativity, and its orbit is decaying exactly as predicted by relativity. The energy is being carried away at just the right rate. So that's an important example. Another thing is a supernova explosion. If a star blows up, that's a very massive object, like the mass of the sun or larger, exploding in a period of about a millisecond, and it turns out that should emit a big burst of gravitational waves. What I'm going to focus on now is black holes, because we have a big project at this university and at 8 other universities to try to compute what would happen if two black holes collide and what would the radiation be that comes out of it. Yeah, please. If you take an object and stop it, yeah, it won't emit any gravitational radiation. Also, it turns out, because of the nature of the theory, if it's like if a star explodes but perfectly spherically, it won't emit any gravitational radiation either. It has to be non-spherical too. Okay. Well, because I'm running short on time, I simply want to say that there is an experiment underway now to detect gravitational waves, which you can't see very well here. Let me just turn this for a second. Wrong one. This one. Middle one. There we go. Okay. This is an experiment called LIGO that is under construction now in Hanford, Washington, and also there's another one identical in Louisiana. They're building vacuum tubes that are point up here, that are 4 kilometers long, and they're going to send laser beams back and forth in here and also along this arm. And when a gravitational wave comes by, it's going to distort the space there, and it's going to cause the laser beams to interact with each other in a different way through an interference effect that I don't have time to explain, although afterwards I'd be happy to talk to you about that. And they should be able to detect gravitational waves with this experiment for the first time ever around the turn of the century. And that's going to be very big news, because it will, first of all, confirm Einstein's theory, and it's going to be picking up new sources of information from the universe that we've never had before. So this is a very exciting field called gravitational wave astronomy, for which not a single piece of data has been taken yet, but we expect this whole field to open up in the early part of the next century. So some of you are interested in getting into science. Here's a new area that's going to be a dynamite thing to work on, because there'll be lots of new discoveries coming out of this. Okay, so let me focus now on black holes. Black holes should be giving us signals of gravitational waves, as I'll explain in a minute. It turns out that black holes come from the collapse of massive stars. if you have a star that's, say, 10 times the size of the sun, it turns out that once it runs out of nuclear fuel that's burning inside it, right now our sun is burning hydrogen and turning it into helium, and the nuclear reactions give a lot of energy off, and that energy provides heat and pressure that supports the star against gravity. So the star, gravity is trying to compress the star, and the nuclear burning inside is providing pressure that's pushing it out, and they're just perfectly balanced. They're almost perfectly balanced. There's slight wobbles in the sun, but it's essentially in equilibrium. But once all of that's burned up, and there's no more nuclear fuel left, then we will run out of fuel, and then the star will collapse. So that's how we can get a black hole. Thanks. We may also get them from the center of galaxies when galaxies are formed. So this is just a basic process, one possibility for how we would get a black hole. But I should stress that a black hole has not been detected without some shadow of doubt. That is, we have lots of observations, but it's not completely sure yet that we've seen one. Is there a question?
Or have to be a certain size and collapse to a black hole.
It has to be larger than, say, in mass. The mass has to be larger at the end of its life than a few times the mass of the sun. Okay? If it's smaller than that, it turns out that there will be some source of pressure that will keep it from collapsing down, basically neutrons inside the star. Okay? Okay, so let me just tell you quickly about the anatomy of a black hole. A black hole is essentially nothing but gravity. Inside, there is a thing called a singularity, where the laws of physics break down, relativity itself breaks down. The curvature, you can imagine, everything in the star collapses down to a single point, so the gravity is really, really intense there. In fact, it's infinite at that point. So what happens is that curvature, density, everything goes to infinity at this point, and there's no way to describe that theory mathematically at that point. So it's a kind of a bad place in relativity and in the universe. Fortunately, for us, there's a thing called a horizon surrounding the black hole that keeps all of the information and all of the trouble we have with that singularity inside that horizon. So we can't actually see inside, and nothing bad from that singularity can get out. On the other hand, outside, we can get these signals coming out. Now, for those of you who've had a little bit of physics, and you know about kinetic and potential energy, you can actually compute the radius of a black hole through a basic Newtonian argument. It says the kinetic energy of a particle is equal to the potential energy. So the kinetic energy we know is 1/2 mv squared, and that's going to be equal to the potential energy, g little m big M, that's the mass of the hole, divided by the radius. And you can solve for the radius, and you get this relationship. It's equal to 2mg over v squared, because the mass of the particle cancels out. So if you let that speed go to the speed of light, so say for a photon, you find that the radius of the black hole is equal to that. And that turns out to be exactly right, even when you do the fully relativistic calculation. Okay. Let me show you a picture. This is an astronomical observation of a black hole. I don't have time to go into details of it, but you can get these kinds of things on the World Wide Web and take a look at them. There are new observations coming from the Space Telescope, the Hubble telescope, that do point very strongly towards the existence of black holes. The basic idea is that you can see this object, you can resolve it to a point where you know it's very, very compact, and you know its mass, and it turns out this thing is millions of solar masses, and it's in a region of space that's very, very small, and we can think of nothing that could stop that from being a black hole. But that's why I say it's indirect. It's not ironclad, because, say, we can't think of anything that would stop it from being a black hole. That doesn't mean that something doesn't stop it from being a black hole. All right. I'd like to focus now on how you would know if you have a black hole. Okay. The main thing, I want to just focus on one thing, gravitational waves. Now, this is something very, very important in all of physics, and in fact in all of science, I'm sure. That is a harmonic oscillator. I'm going to explain basically that a black hole is like a little oscillator that's oscillating back and forth when it's slightly disturbed. So if you have a black hole and you take a pebble, so you're an astronaut outside the black hole and you want to do an experiment, you say, gee, I wonder what would happen if I just threw this rock into that black hole. You know, I often like to do that when you're on a bridge, throw it into a pond. When you throw it into a pond, what happens? There's a little splash and then there are ripples that come out, but it all dies away and it ends up just being a nice smooth pond again. On the other hand, if you were standing at the edge of the pond and you saw the ripples coming, you could measure those ripples when they got to the edge, and you could determine by making careful measurements that somebody just threw a rock in or there was some disturbance at that point right over there, and you could even probably calculate how big of a stone was thrown in there by the amplitude of the waves that came by you. It's the same basic idea here for a black hole. Turns out if you're in a spaceship outside a black hole, throw a rock into it, the black hole doesn't blow up or anything, it just it gets perturbed, and it just sort of wobbles around a little bit, and it dies down, and it ends up as a spherical black hole again. And this is the basic picture. Throw a pebble in, it's distorted, it emits waves not from within the horizon, but from a region just outside the black hole where it's still fair for signals to get out. They propagate away, and essentially you get what we call the ringing mode of the black hole. It sort of rings like a bell. And when I said this last year, exactly at that time, the bell went off just by coincidence, but no luck this time. So anyway, if you studied the harmonic oscillator in physics, you know, if you take a pendulum and you just sort of give it a little push, it'll just start to rock back and forth, and eventually it will decay away because of friction, and then it will stop. Same thing, if you hit a bell, it will ring with a certain frequency that depends on the mass of the bell and the shape of the bell and so forth. And as the sound waves are carried away, then the energy of the oscillations in the bell die down, and eventually it settles down and it's just quiet again. A black hole is the same thing. So this is really one of the most important ideas in all of physics, the harmonic oscillator. And it works for black holes, bells, and many other things. So here's an actual signal that you would see if you perturbed a black hole. This is the time, and this is the amplitude of a wave. So if you perturb a black hole by throwing a stone into it, you'll measure a wave that sort of oscillates like this and then dies down. Okay, I know that I'm not using my other projector, but I think I'm running low on time, so I want to just get straight to the punchlines here. Okay, so how do we study a black hole? Well, I've told you that the equations are very complicated. So, and they're sort of impossible to actually work out solutions like you can for simple algebraic equations that you work out, say, in some of your classes. These equations are incredibly complicated, but again, I want to point out that there's a simple idea behind them, and it says, here is written in kind of fancy notation, these are the Einstein equations. It says that the gravitational field, this is all on the left-hand side, there are actually 16 equations here, although the symmetries make it only 10. So there are 10 complicated partial differential equations for the gravitational field. And on the right-hand side, there's matter. And the basic way of understanding this is that the matter on the right-hand side of this equation tells space-time how to curve, and the space-time tells matter how to move. And that's the underlying philosophy of the equations. To show you how complicated they are, here is one of the terms in the equations. And these are complicated derivatives of functions. If you know calculus, they've been differentiated. They're highly nonlinear. That's one term. This is a continuation. It's page 2. Continuation is page 3. This is all worked out by computer algebra programs like Mathematica. There are literally tens of thousands of terms in these equations. They're very, very complicated. So you wonder, how on earth could you ever solve those? Well, the way we can solve them is by getting very large computers, writing a computer program that can give us solutions to such equations, and solving them. Now, the idea is that computers have gotten so powerful in the last 5 years that for the first time we can actually try to solve them. And here's an example. I'm going to go through this rather quickly, but here's the speed of what was called a Cray YMP computer that a few years ago was the fastest machine in the world. And it could do about so many billion, that's a gigaflop, billion floating point operations per second, and it had, a couple of hundredths of a billionth of a billion words. So it had basically some megabytes, basically what you can get on a fancy Pentium workstation a day. That's what a Cray computer had just a few years ago. This computer costs $15 or $20 million. A Pentium just costs about $2,000, maybe $3,000 for a lot of memory. So that's an idea that, in a sense, a Pentium is coming up to the speed of a Cray. It won't be very long for it really be the same speed as what a Cray was a few years ago. But this is 1993, so millions of dollars, and you get a computer like that. Well, if you actually take the next generation of computers that came out the next year, here's the entire graph that I just showed you, and you can see we're now into doing actual tens of billions of calculations per second and much more memory. And you can just keep scaling it up. It turns out if you take hundreds of processors, like say Pentium or PowerPC, Macintoshes, processors of that speed, and you put hundreds and hundreds of them together. Here's the previous graph that I showed you all down in the corner, but you see we're just scaling right up. We have a machine at NCSA called the CM5 that has 500 processors working in parallel. So that means the code could be 500 times faster, as it would be on each individual one. And it just keeps going. I could keep drawing these graphs, but here's where the Cray YMP is. From a few years ago, a $20 million computer is essentially on the origin. It's just so slow you wouldn't even want to use it anymore. But now by looking at parallel computing, putting more and more cheap processors together, you can get much, much faster. So you can solve problems that a few years ago were unthinkable, like the Einstein equations. So I want to simply say that we have developed codes for solving the Einstein equations that take advantage of these new computers. That's just, it's revolutionizing computational science, physics, biology, and many fields. And I want to show you some movies now of what happens when you take black holes and distort them or collide them together. The first one I'm going to show you is a black hole that is surrounded by a ring of gravitational waves. Now, the gravitational waves, this is a kind of a theoretical problem. We just wanted to see what would happen if you distorted a black hole. How would it respond? The gravitational waves, because they carry energy, also have gravity, and so they sort of distort the black hole. Then the black hole distorts the waves. Some of them get sucked in, some of them leave, and the black hole starts to oscillate, as you'll see, and it ends up as a spherical black hole in the end. Okay? So let me show you a movie of this. Oh, yeah, sure, thanks. Okay. All right. Here is the first movie. Now, let me pause it for a second. What we see here is a black hole that's been distorted by gravitational waves. This ring in the center, what you can probably see up there, there's a ring surrounding a sort of a disk in the middle. That's the horizon of the black hole. And these were calculations that were done on a supercomputer like the Cray YMP, actually, that we did a few years ago. This is not a fully general calculation. It's axisymmetric, which means there's a symmetry axis right through here. You can see it kind of looks the same on either side. And if you were to rotate this thing around, you'd see these sort of donuts of gravitational waves surrounding a black hole. Because this wasn't a fully 3D problem, we could do it on a supercomputer of a couple of years ago. But now the full 3D problems are requiring much, much bigger computers. So what happens when this system evolves, which we've simulated on the computer, is that some of the waves go into the black hole, but you can see, I told you there's a little region right outside the black hole where gravitational waves come out. And right here, you can see these pulses. That's the ringing radiation from the black hole. So it's been disturbed, it's oscillating, and then there's a radiation signal coming out from it. And when LIGO comes online in about 5 to 10 years, we should be able to measure these kinds of waves coming out of a black hole, or coming from just near a black hole. Now I'll show the same simulation again, just so you, in case it wasn't very clear. Here it goes. We're going to let it go in time. You see some of the radiation comes in, but immediately some of it's going out, and you can see the black hole. You can't really tell that it's oscillating, but you can see the result of the oscillations. The waves are coming out here like so. Now, I want to speed through and show you the next simulation, which is very similar. The same thing. Now we're going to focus just on the inner part of the black hole. These peaks are now just the height, the wave amplitude of the waves. And you can see here the horizon itself is kind of flapping up and down in this picture, and it's actually generating these waves just outside that are coming away from the black hole. Okay? So I would like to fast forward through here. Don't really have time to go through the whole thing. There's actually, I have about 20 minutes of video here. And if people actually would like to get a copy of this, you can see these things on our web server, or you can also see them, you can get a copy of the videotape, and I believe there's going to be a part of this video put at the end of the lecture as well. So here's another calculation where you can see the waves in another way, propagating away from the black hole and also going inside the black hole horizon there. Now here's a more complicated case. Right? You can see waves in a more we put a larger gravitational wave there, more complicated spatial structure to it, and you see lots and lots of waves coming out. Here's a picture that shows the same thing, but with the height being the amplitude of the wave, and you can see the thing is really wobbling around because of the highly distorted nature of it, but it starts to settle down, and towards the end you'll see it's just a nice quiet black hole with waves far away from it. And that's essentially what happens. Now, I have also a video of colliding black holes, but they actually look very similar. So I think I won't show them. What I'm going to do is just conclude, show you a picture. Two colliding black holes. Yeah, there's a question. The disturbance in this case was caused by, just by hand, we put some energy around the black hole, and we wanted to see how that black hole would respond to having that energy. That was our version of a stone that we threw into it. We threw some gravitational wave energy into it, and we just sort of know how to set that up as an initial condition, and then we watch that system evolve after simulating on the supercomputer. In this case, we have two black holes that will be colliding, and what happens is the black holes distort each other. They collide and form one highly distorted black hole like the one I just showed you, and then they settle down to a single black hole in the end. So essentially the movies look the same, so I don't have time to show them. What I'd like to do is just summarize, and there are a few important points that I want everybody to remember. So everybody should wake up, and you can get everything out of the talk by just these nuggets, all right? The first one is that Einstein has a very great theory of physics, and we're really on the verge of solving the equations that he left for us for the first time in this entire century since he wrote them down. They're almost, and now it's about 80 years that these equations have been around. Those equations are going to tell us a lot about astrophysics, about the study of the universe, and about the theory of relativity itself. Scalable computers like those graphs I showed you are going to allow us to solve these equations, not only relativity, but many other fields of physics and computational science as well, because they're bringing power that was unthought of just about 5 years ago. And one thing I didn't really emphasize was that prior to this parallel computer age, computers were getting a little bit faster every year, but not that much faster. But now they're just exploding in power, and now finally we'll be able to solve these things. There's a new experiment called LIGO that's going to detect gravitational waves if they really exist. That's, of course, we believe that, but we have to prove that experimentally. And that should be seen probably by the end of the decade. We're going to see black holes oscillating normal modes, and we're just now at the stage where we can do three-dimensional calculations. I didn't show you a three-dimensional one, but we're just barely able to do that with present technology. So just to completely summarize in a picture, I think this is a simulation we did in a virtual reality environment where we're trying to study gravitational waves in 3D. So you've heard about virtual reality. We're actually trying to use it to study science here in gravitational waves, an experimental visualization system we have at NCSA. And what I see is computational science is really reaching out in all directions, and it's making a huge impact on relativity and many other areas of physics. So thank you.